Hi, in this video, we want to take a look at simple correspondence analysis. Okay, so we're in the situation that I have a contingency table, and for this video, we're going to just use 2 dimensions. And on my contingency table, I run a chi-square test, and I conclude that we do not have independence or we do not have homogeneity. Okay, so then what do we do? How do we analyze this? Well, that is called correspondence analysis. All right, so this example is modified code from Modern Psychometrics with R by Mayer, and here is the website for the R code. Okay, so like I said a moment ago, I've got a 2x2 contingency table. I run a chi-square test, and I conclude that we do not have independence between rows and columns. All right, what do we do? How do I analyze it? How do I proceed? Well, let's find out. Okay, so let's go ahead and let's use some fictitious data. So for this data, we have 3 different fans, Horst, Helga, and Klaus. And we have 4 bands, Slayer, Iron Maiden, Metallica, and Judas Priest. And we have the count for the number of times that these fans went to these bands' concerts. Okay, so here's what we've got. Here is my table. And so you'll notice that I have a matrix storing the data, and then I convert the matrix to a table. And because tables are how chi-square tests like to proceed. Okay, so I've got my information here. And so we can see, like Slayer had 9, 13, and 15. And then Iron Maiden had 12, 1, 4. Metallica 8, 6, 23. And Judas Priest 1, 20, 18. Okay. And we can also see the numbers for each of the fans. Okay, well, first thing I'm going to do, I'm going to check chi-square test. Are the counts in terms of rows independent of the counts in terms of columns? That's my first question. And so if I have independence, then each of the counts would be approximately proportional to the number of counts in each column and proportional to the number of counts in each row. So this entry here, if I have independence, this count would be independent of the sum or would be proportional to the sum of these 3 and the sum of these 4. And that's how we work through the chi-square test if I want to do it manually. All right, so let's go ahead and actually just run the chi-square test. Let's take a look. Okay, so my test statistic is 40. That's going to be pretty big. All right, so here my degrees of freedom is going to be 4 minus 1, 3. 2 minus 1, or sorry, 3 minus 1, 2. So 2 times 3 is 6. And so remember that this comes from a chi-square distribution, and our degrees of freedom will be equal to our expected value. So 40 is much bigger. All right, so I see that the p-value is very, very small. All right, so I conclude that we do not have independence between rows and columns. Okay, well, what do I do now? How do I proceed with that? If we conclude that there was independence, then that's it. There's not really much of a story to go any further. Now I want to dig deeper. I want to go deeper into this. Okay, well, let's take a look at what's going on. So if I go ahead and I extract the residuals from my chi-square test, we can take a look. Okay, all right, so what jumps out at me? Look at the biggest values first when you look at this situation. Iron Maiden and Horst was much greater than the expected value. Okay, and let's see, we see that Judas Priest and Horst was less than the expected value. And then Helga is much greater. Helga going to Judas Priest is greater than the expected value. And then from there, they start getting smaller in magnitude. And so, well, let's see, let's go ahead. So Helga and Iron Maiden is lower than the null hypothesis would say. Then Helga and Metallica is lower than we would say under the null hypothesis, Klaus and Metallica is greater, and then Klaus and Iron Maiden is less. Okay, so let's go ahead and visualize this. I want to visualize this with the mosaic plot. Okay, so we're going to use the VCD package, and we're just going to use the mosaic function. Okay, and I set this up so that here we have rows of our mosaic plot going by band. And so here the residuals aren't too big. Residuals aren't too big and whenever I have gray, but I can see that the Iron Maiden and Horse is much greater than expected. And then Judas Priest and Helga is much greater than expected. So here it goes Horst, Helga, Klaus, Horst, Helga, Klaus, Horst, Helga, Klaus, Horst, Helga, Klaus, and so on. Okay, so we can see that Judas Priest and Horst is much lower than we would have expected. Okay, now I go ahead and take a look at this in the other way, where now I put the fans as the rows, and you can see that the bars are consistent going left to right in this manner. And so we see the same information, but it's presented by, so previously we had presented by band, now we have it presented by superfan. And both are equally correct for what we're doing. All right, so now let's go ahead and look at our, let's go through, let's go ahead and get the proportional table. And I meant to print the table here. I made a mistake. Okay, but we'll just rock on. All right, so now if I take the proportional table and I want to look at the margins with respect to the first dimension are the rows, those are the bands. Here we can see the proportion of times that it's Slayer, Iron Maiden, Metallica, Judas Priest. Now, something about this. This is the proportion of times that one of these three went to one of these four bands. Now, in this analysis, we could have had Horst, Helga, and Klaus at the same concert. And so the interpretation is a little bit sticky because we have this overlap aspect, but we're going to go ahead and proceed nonetheless. So we can see that, Judas Priest had, just under a third of all of the attendance. And then we can see that Slayer and Metallica had over a fourth, and Iron Maiden had the least. Okay, so now so that is going by row. Let's do the same thing by column. Well, we can see that Klaus is, over 40% of the attendance was just Klaus alone. All right, so it looks like Klaus is the guy that's going to the concerts the most. And then Helga is a little bit less than a third, and Horst is less than a fourth. Okay, so now let's look at the conditional relative frequency of rows. All right, so what I want to do, you'll notice that after I do the prop table, margin one means I'm interested in going by row. If I add these up, I'm going to get 1. If I add all of these up, I'm going to get 1. If I add all these up, I'll get 1. Yep. And if I add all these up, I'll get 1. So here, this is showing that when a Slayer was attended, so this is where the understanding of this gets kind of sticky. So if I was to randomly pick, someone who attended a Slayer concert among these three people, and I randomly pick one of the times that it was attended, it would be a 40% chance I would grab Klaus. Now, remember that this is a convoluted interpretation because we could have had Horst, Helga, and Klaus all at the same concert. Now I can do the same thing for columns, and here if I add up the columns, it adds up to 1. Now if I go through and I look at the average row profile, I'll notice I'll get the same result I had previously. If I do average column profile, I'll get the same result I had previously. Okay. So now let's go ahead and look at a 3D plot of our data. All right, so since I've got 3 people on there, since I've got 3 columns, I can go ahead and I can actually take advantage of this and start plotting the things in terms of 3 dimensions. It gets more complicated if I had more variables. So we'll go ahead and do that. And so the package I'm using is plot3D. And we're going to use plot3D, scatter 3D. And here's all that beautiful code. It's quite a bit. Phi and theta tells you the angle that you're looking at. Phi and theta are the common notation in Calc 3, by the way. And so these tell us the angle at which we're looking at 3-dimensional plot. If it was an interactive plot, I would be like rotating it around, moving up and down, but this one's static. And here we're adding some points. Points along the axes. We're adding some more points this way. Or so no, we're adding lines. And let's go ahead and add some text. And now we can see what's going on. So the lines help us interpret what's going on the position of the dots. Because this is a 2-dimensional representation of a 3-dimensional object, it's going to be hard to actually judge the height of these points and where they're hovering above, and makes it a little bit easier to work with it. My opinion is that 3-dimensional plots, from a math perspective, they're very, very alluring, but when you get into them, you actually start working with them, they're not worth your time. So I don't bother with this type of plot. And we can see that we have an axis for each of our superfans. Now, another way to visualize this is a ternary plot. So what we're going to do here is that we're going to so for each row of our data, we're going to take that probability vector that we had previously, where each row was a probability vector. Then I'm going to plot each of those length 3 vectors on a triangle, where the triangle represents, each position on the triangle represents a probability vector of length 3. And that's called a ternary plot. All right, now, to do this, we're going to need to do a lot of data prep to get things going in the right way. So, I need a data frame for my data, so I can just do the ggplot format. Here, I'm doing my proportional tables. And then here, I'm working out details of some lines I'm going to plot in a moment. And here's the actual plot. And so you'll notice that each of my superfans ends up being a variable for the ternary plot. All right, and so now we have Iron Maiden, Metallica, Slayer, and Judas Priest all plotted here. So if, let's say we were in the situation where only Klaus went to a particular band, then in that situation, that band would appear in this corner. If only Horst went to a concert like Helga and Klaus did not, then that point would be in this corner. If Helga was the only one that went to the band's concert, Horst and Klaus did not, then it would be in this corner. Now, if it's along this edge here, this is saying that Helga did not go to any of the band's concerts, and Horst and Klaus did, and the position says proportionately how many each. This line here indicates that Klaus was not involved at all, and so if it's up here, it's Helga was present at the concert more than Horst. Here, Horst would be present more than Helga, and then correspondingly, if a dot is along here, Horst did not attend any of the concerts. So we can see that Horst attended very few Judas Priest concerts. We can see that Helga attended very few Iron Maiden concerts. But since it's not on the edge, we can see that they did attend some, just not as many as the other two. And we can see that between Horst and Klaus, Horst attended a lot more Iron Maiden concerts because it's closer to Horst. And here we can see the overall average, that dot right there. And so we can see that Slayer as a band is more consistent with the average than the other three. And then Metallica is the second most consistent with the overall average. Iron Maiden is the least consistent. All right, so something that we might want to do is take a look at the distance between bands and the distance between bands and center. Okay, so if I go through and I take the Euclidean distance, which is what I'm doing right here, that almost gets it right. But there's a problem. I need to rescale things in terms of the chi-squared expected value. And that chi-squared expected value is right there. So I need to rescale things to make sure that I get the right interpretation, and we get 1.1. All right, now here I'm doing the Euclidean distance between Slayer and Judas Priest, rescaling by the rescaling by the overall average. So to adjust for the expected value, I see that they are closer than Slayer and Iron Maiden. And then when I look at Iron Maiden and Judas Priest, these two are the farthest from each other. Now, if we look back up here, Iron Maiden and Judas Priest are in fact the farthest apart. Now, if I'm interested in the distance from center to a band, then I just do the same thing, but I'm subtracting off by AR profile. And just to remind us what that is, I'm going to go scroll up, find where I put that, so we can see that. Yeah, so the AR profile is the same as the column averages in terms of a probability vector. So it's the average, so it's like the probability for each of the columns marginally. Now, where was I? Okay, so now let's visualize the correspondence analysis using singular value decomposition. All right, so I want to do analysis of correspondence with the Anacor package. My table is superfan, and I want ellipses. All right, so now let's go ahead and take a look at the results. If I run this, and so here, remember, I had 40 as my chi-squared test statistic before. All right, the sum of the eigenvalues, and this is called the total inertia, is 0.3. And here are the eigenvalues for the principal components. And we can see, and so this will always be going off of the minimum of the dimension minus 1 will be the number of eigenvalues I have because of the whole, because for the eigenvalues, I need to be using a square matrix. We're multiplying by the transpose to get the square. And because of degrees of freedom, because everything adds up to 1 for this analysis, then I have to subtract off degrees of freedom, and that is why I only have 2 eigenvalues instead of 3. Now here's my root mean squared error for rows. Here's my root mean squared errors for columns. That's pretty small. So this is looking at the idea of using something similar to principal component analysis. How far off or how much information do I lose if I go ahead and just go with 2 principal components? And the first dimension accounts for 84% of the variability. The second dimension accounts for 16. And then if I want to do a z-test instead of, if I want to do a z-test on this, I can get p-values. And so that gives me an idea of what's going on for this. Now here's my plot. Now it's very, very tempting to look at this and go, hey, Horse and Iron Maiden, Helga, Judas Priest, Klaus, and Metallica. We can't do that. That's actually an incorrect interpretation. It's unfortunate that R puts these on top of each other. Really, we need to treat these as 2 separate plots. This is the principal component analysis of the bands and the principal component analysis of the superfans, and we need to interpret them as separate items. That's very important. So if I look at the bands, I can see that Metallica and Slayer are at about 0 along the first principal component. Iron Maiden and Judas Priest are on opposite ends of the first principal component. In terms of second principal component, we see that Metallica is the only one that's negative and the other 3 are about the same. Okay, so now if I look at the fans, we see that Horst and Helga are the farthest out in terms of the first principal component. So the Horst and Helge are probably the two fans that are the most different from each other. And then Klaus, along the second principal component, is the most different from the others. Now, one of the reasons why we cannot trust this in terms of interpreting both plots at the same time is because it's possible for reflections to happen this way. So after I get my band symmetric correspondence analysis map, once I get the plot down for the bands, the first principal component could be like this, second principal component can go like this, either way. And so there's 4 different possibilities, and the plot doesn't tell me what's actually going on. I have to dig a little bit deeper. Now I can figure it out by looking at the original table, since this is such an easy example. All right, so let's kick it up a notch. Let's make this just a little bit more interesting. What we're going to do, we're going to take the research profile of a bunch of Harvard psychologists. And what we're going to do, we're going to do text analytics. We're going to get a bag of words model to get a document term matrix. Then what we're going to do, we're going to do the correspondence analysis on the document term matrix. All right, so what we're going to do, we go ahead and load the data. This is a document term matrix of the terms that appear in Harvard psychologists research profiles. Now I'm going to run the analysis of correspondence on it. And so this is built up, this is very similar to principal component analysis because it's using singular value decomposition. And so because of that, there's going to be some, I feel like non-negative matrix factorization actually would be a better choice, but that doesn't give me orthogonality, and it's a different interpretation. So I can see why the author chose this. I would have done it just a little bit different, but yeah, I feel like this is still correct. And so now I've got each dimension of my principal component analysis. And we can see after, so if I say that like 0.1 is my cutoff for my dimensions, after 2, I'm not picking up anything else. And we can see that they get pretty small after a while. So now what I want to do, I want to plot all the Harvard faculty so we can see that our dimensions, the smaller of the 2 dimensions is going to be 29. Remember, it's -1 because the whole chi-squared degrees of freedom thing. All right, and so now I can see that like the orangish, reddish colors, maybe coral, I don't know. Those are the terms coming from their research profile, and the researchers are the ones in teal. Okay, so this kind of gives me a feel for what's going on. We can see that a lot of the data, or a lot of the terms, are clumped up in this region, and we can see that things kind of stretch out to balance it out. Remember that principal components are always orthogonal to each other, and so that kind of forces, so having everything clumped up here means that to a large extent these guys are kind of counteracting that balance. It's kind of like balancing it out. And you know, we can see self-control over here, like everything over here is kind of tight. Well, this is kind of pulling things out. We can see the structure is you know, very different than the rest of the terms over here. Now, when it comes to the second component, we see language and self-control are very different, but we see that to a large extent, in terms of the second principal component, most of the terms are relatively in the same neighborhood, you know, plus or minus. Now, in terms of researchers, we see things very similar. And this kind of gives us an idea of where each researcher's focus is without having to go through and read all of it. So if I wanted to, so I know that Nakayama is going to be very different in research than, you know, Buchholz. And so that gives me, you know, so if I was looking to collaborate with one of these psychologists on something, I know that if Nekayama was the guy to work with, Buchholz probably not. And here we can plot again, but here I'm zooming in on the tighter ones, and we can definitely see that things are kind of in this cloud going on. We can see like health is very different from like functional over here. We can see Pinker is very far from Gershman. All right, well, that's all I've got for you. Take care and goodbye.